Linear programming is when you're trying to, it's usually used in business when you're trying to maximize a profit or minimize a cost. So linear programming involves inequalities and an objective function. So an objective function can be a profit or cost equation. So usually in business, you want to maximize the profit and minimize the cost. Your constraints are your inequalities. So in business, you might have a constraint as far as the quantity of items that you have, or the cost that you have, or your budget, or your time. So time, your inventory, those are all can be inequalities. And the feasible region is going to be your solution to your constraints. So when you write all of your inequalities, you're going to shade them like we have done previously, and where they overlap is going to be your feasible region. So this is an example of a feasible region right here. So these are called the vertices of the feasible region. So if you can see on this linear programming problem, there's a line that was right here that was shaded less than. There was a line right here. There was a line right here. And there's a line right here. So there's actually 4 constraints in this problem. So in this first example, we already have an objective function. So this could mean something like profit equals 5 times x plus y. Which ordered pair maximizes the objective function? So what you're going to do is I'm going to write down the vertices of the feasible region. So the vertices are A, which is at 0, 500, B, which is at 0, 1,000, C, which is at 500, 800, and D, which is at 1,000, 0. So I'm going to use my objective function and plug in this for x and this for y and see what I get for p, my profit. So this is going to be 5 times 0 plus 500. This is going to be 5 times 0 plus 1,000. This is going to be 5 times 500 plus 800. And then this will be 5 times 1,000 plus 0. So the value at p for the first one is going to be 500. Second one's going to be 1,000. The third one is going to be 2,500 plus 800 is 3,300. And the last one's going to be 5,000. So the question is, which x and y maximizes p? So because we're trying to maximize and not minimize, maximizing it is going to be the ordered pair 1,000 and 0. Okay, example 2. Graph the system of constraints. Then find the values of x and y which maximizes this objective function. So first one is x is greater than or equal to 0. So I'm going to shade to the left, or to the right, I'm sorry. And then the second one is y is greater than or equal to 0. So that's going to be shading above. So it's kind of messy so far. And then when I'm graphing x plus y is less than or equal to 4, I'm actually going to graph by intercepts. So I'm going to find the x-intercept, which is 4. And then I'm going to find the y-intercept, set x equal to 0, which is 4, too. So I realize I think I went over to 5. So I'm going to graph it at 4, 0, and 0, 4, and then connect with a solid line. And I'm going to shade less than. So far we have, in our feasible region, we have this triangle right here. Okay, then I'm going to do the same thing with this equation. So I'm going to find the y-intercept, which set x equal to 0, so that's 6 on the y-axis. And then set y equal to 0, x is 3 on the x-axis. So connect the dots. It's best to do a ruler. I don't have a ruler right now. And now I have, actually, should have went through here. Okay, so now I'm going to zoom in. It's kind of messy to see right now, but my feasible region is going to be this region right here, which is here, 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 and here. So this black part. So if you have a ruler, it's easier to do. So my vertices are going to be 0, 4, 0, 0, 3, 0, and 2, 1. Okay, so those are my vertices. So I'm going to write these over here. So my vertices are 0, 4, 0, 0, 3, 0, and 2, 1. So I'm going to plug them into 30x plus 50y. Okay, so this is going to be 30 times 0 plus 50 times 4. This is going to be 30 times 0 plus 50 times 0. 30 times 3 plus 50 times 0. 30 times 2 plus 50 times 1. So the first one, the zeros are going to this will cancel out. So this will be 200. These will both cancel out, so this will be 0. This will be 90, and this will be 60 plus 50 is 110. So the ordered pair which maximizes C is going to be the ordered pair 0, 4. Sometimes you have to come up with your own objective function. So an ice cream shop makes $1.25 on each small cone and $2.25 on each large cone. So remember we talked about each, how that would be multiplication. On a typical Saturday, it sells between 60 and 80 small cones and 120 and 150 large cones. The total sales have never exceeded 200. Have never exceeded is an inequality. So my variables, it has, even though it doesn't have a question down here, actually let's look at the bottom here. The question at the very end is how many of each type of cone. So we're going to let X be the small cone, and then Y be the large cone. So what are our constraints? What are our limitations? Well, our limitations are that we need that cells between 60 and 80 small cones. So 60 is less than or equal to X is less than or equal to 80. And the other constraint is that the large cones are between 120 and 150. Also, we know that the total number of cones have never exceeded 200. So this means that X plus Y has to be less than or equal to 200. So sometimes in linear programming, you have to have a minimum value. So sometimes you need to write in X is at least 0 and Y is at least 0 because you can't have negative number of items. But in this case, we already have a minimum value of 60 and 120, so I don't need to write those. So the next part, graph these. So I need to come up with a scale. So I'm noticing that when I find my X and Y intercepts over here, X and Y are going to have to both go across up to 20. So 200, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So this is going 20 across. So I'm going to be in the first quadrant, and I'm going to graph this one first. So the y-intercept is 20, and the x-intercept is 20. And you really want to take a ruler and connect them. And so that's going to be less than. Then x is between 60 and 80. So I'm going to go up to 6 right here and 80 and make a strip right here. And then I'm going to go between y is between 120 and 150. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12, 13, 14, 15, right here. So the vertices of the feasible region are going to be this right here. I'll do a different color. So it's going to be this vertice, this ordered pair. Never really shaded in between here so you could see it. But this ordered pair and that's it. So I'm going to zoom back out so we can kind of see what these vertices are going to be. So I went over 60 and up 12 or 120. So it's going to be 60, 120, and then over 60 up 15. So 60, 150, and then over 80 up 120, and then over 80 and then up 13 or up 130. So 80, 130. So I'm going to write these in here. So my vertices are, I actually have 4, so we're missing one right here. So it's going to be 80, 120, 80, 150, 60, 120, and 60, 150. So I'm going to plug in, I'm going to pause it, and I'm going to plug it into my objective function. So actually I got to write the objective function. So the objective function has to do with the amount of money that we make. So our profit's going to be $1.25 per small cone plus $2.25 per large cone. So I'm going to plug in X and Y into each one of these and write my profit. So I took each of these X's and plugged them in for here, and each Y at each point to get the profit. So the profit that maximizes is this. So how many of each type cone should be sold to maximize the profit? We want to sell 80 small cones and 150 large. And that's going to maximize the profit. So that's how linear programming works.